Hi, everyone, and welcome to week 6 of your online learning. This week, we're going to look at acids and bases. You should already have a good idea about acids and bases and how they work already, just from everything that you've ever done in basically science before. So we'll start with acids. What are some properties of acids? Well, the most important properties of acids are you're going to have that they're sour. And we should know that the pH is going to be less than 7. There's a whole bunch of other different things, but those are the most important things that you should take away with this. Do you know any acids? You have used acids before in class. You've got hydrochloric, you've got acetic, you've got lots of different acids that you know. Remember, acetic acid is vinegar, so we have that one in our house. Now, it is important to note that acids are symbolized by either the H plus or the H3O plus. So if you see that, that means it's going to be an acid. And remember, when we did acid nomenclature, it always has an H in front. Bases, bases are bitter. Okay, and their pH is going to be greater than 7. Bases, anything with an OH at the end is going to be basic. There are other compounds that do not have hydroxides that are bases. For example, ammonia is a base, doesn't have an OH, but it is a base. And again, OHs at the end, the hydroxide ion symbolizes that you have a base. Now, there are 3 different definitions of acids and bases. The first one, you've got an Arrhenius acid and base, where an Arrhenius acid gives off a hydrogen, an Arrhenius base gives off a hydroxide ion, and that's when they're put in water. The best definition, the most inclusive definition, would be a Bronsted-Lowry acid and base. Bronsted-Lowry acids are substances that donate a proton, and the bases are accepting a hydrogen pair. So those things will include ammonia. Ammonia is going to be a Bronsted-Lowry base because it can accept a hydrogen and become the ammonium ion. Whereas, according to Arrhenius, ammonia is not a base. And then the Lewis theory of acids and bases is a much more inclusive definition. It's a little more complicated, but we know Lewis from his Lewis dot structures. So Lewis acids accept an electron pair, while Lewis bases donate an electron pair. So when we talk about acids and bases, we're going to talk about the strength of an acid and base. Now, a strength of an acid or a base is not connected to its concentration. Remember, concentration is molarity, okay? So you put the brackets, that has to do with concentration. So you can have a strong acid with a very weak or low concentration and a weak base with a strong concentration. The important thing here, the strength of an acid or base determines how well it will dissociate or break up into its ions. Strong acids and bases dissociate completely. And then there is a list of the strong acids and the strong bases. So if you see that, know that those are going to dissociate completely. So hydrochloric, chloric, perchloric, hydrobromic, hydriodic, nitric, sulfuric acids are all going to be strong acids and dissociate completely. Strong bases are group 1A and 2A hydroxides. Those are going to be the strong bases. So we talked about equilibrium expressions and the equilibrium constants I think that was last week, the Ks. And so for acid dissociation and base dissociation, you can have a Ka or a Kb, and it just tells you how well they dissociate. So if you have a strong acid or a strong base, their dissociation constant is going to be 1, greater than 1, because it's going to go to the products. And you can see your dissociation constants here. For an acid, it's going to be the hydrogen ion times the anion, so that's why it's negative, over the acid. And then for the Kb, it's going to be the protonated base, which is going to be whatever the base was with a hydrogen on it, the hydroxide ion over the base itself. So weak acids and weak bases do not dissociate completely, and so their Kas and Kbs are going to be less than 1. So examples include acetic acid and ammonia. So I'll show you what that looks like. So you take acetic acid, which we know is the acid. If I add it to water, it's not going to dissociate completely, and therefore I'm going to have a double-sided arrow. And so acids give off hydrogen. So this is actually the hydrogen that gives off, and it's going to go to the water. So that water is going to turn into H3O+, which is a hydronium ion, and the acetate ion. I can do ammonia below. So NH3, you add it to, oh boy, you add it to water. We all know what water is. Again, since it's weak and doesn't dissociate completely, you're going to have a double-sided arrow. And so the water here, we know that this is going to be the base. And so the hydrogen is actually going to give off hydrogen, and I'm going to have the ammonium ion and the hydroxide ion. So this is how I know it's an acid and a base. For acetic acid, you're going to get hydronium. For ammonia, you're going to get hydroxide. Okay. So conjugate acid-base pairs when two substances that are related by donating and accepting a hydrogen that are in equilibrium with each other. So we can do that for these examples. So technically, acetic acid was the acid, and the water in this case accepted that hydrogen, which makes this a base. Over here, the products of an acid-base reaction are going to be conjugates. So H3O+ is going to be the conjugate acid. CH3COO- is going to be the conjugate base. And remember, if acids donate, bases accept, the H3O+ can donate because it's got that, and the CH3COO- can accept because it's negative. And that's why it's a double-sided arrow. Down here, and so you go from the acid to the conjugate base, the base to the conjugate acid. That's how they are related. Same thing. Now, in this case, the water is technically an acid, and so it will give off the hydrogen and go to the ammonia, which will turn into the ammonium ion. Since it's positive, it's going to be the conjugate acid, and the OH- is going to be the conjugate base. And that's how they're related. Okay. So compounds that are amphoteric, so that's going to be a new word for you, can act as either an acid or a base. In that previous two examples, in one example, water was an acid. In one example, water was a base. So in that case, it is amphoteric. Water also does this thing called self-ionization. So it can react with itself, basically, to turn into its two ions. And that's called, and we can get a Kw, which is the water dissociation constant, because it will dissociate. Tells you how well water dissociates. We can use it to determine a Ka or a Kb for any acid or base. So Kw is always the same. It's this is the value at 25 degrees Celsius. The Kw changes slightly when the temperature changes, but that's what we're going to always assume. That's standard conditions. So it's the concentration of a hydrogen times the concentration of hydroxide, and Kw is 1.0 times 10 to the negative 14th. And you can take a Ka times a Kb equals Kw. Again, this is always the same. If you know one, you can find the other. Now, pH scale, you should know it goes from 0 to 14. 7's in the middle. From 0 to 7, this is acidic. 7 is neutral, and 7 to 14 is basic. Question for you. Can you have a pH less than 0, so a negative pH? Can you have a pH greater than 14? Yes, you can. So pH can be less than 0, and the pH can be greater than 14. It's a possibility. This is just not set in stone. This just gives us a good endpoint, since 7 here is going to be considered neutral. So the next thing is asking us to calculate pH. So an important equation, 2 important equations. I'm going to write them up here. pH is equal to the negative log of the H plus concentration. And then inversely, if I wanted to find the H plus concentration, it's going to be equal to 10 raised to the negative pH. So those are your equations, very simple. So you can just plug them in. You have the H plus concentrations. All you have to do is plug them into this equation. Now, a hint for you. I don't know if it's a hint or a trick or whatever it is, but something that's very useful. If you have a hydrogen ion concentration where 1 is the whole number and then it's times 10 to an exponent, the negative exponent is the pH. So if I was to do this one, the answer for the pH for this one is going to be -5. The pH for this one is going to be +7. Don't believe me? Put it in your calculator. But trust me, it works. And it works every time if that whole number is 1. Keep in mind, if it is not 1, you can still have an estimate. So for 3.1 times 10 to the -5th, I should know it's around -5. I should know this one's around +7. And you can just plug it in. pH is equal to the negative log 3.1 times 10 to the 5th. And then this one would be pH is equal to negative log 2.0 times 10 to the -7th. Now, there are rules for doing sig figs with pH. We're going to skip them. If you choose to take my class next year, we will learn those rules, but they're very simple. But we got enough things going on. We're not going to worry about it. So plug that into your calculator. This answer is -5.49. This answer is +6.70. Okay, so you can see it was about 7. It was about -5. Okay, it gives you an idea if your answer is going to be somewhat close. Unit-wise, no units for pH. Okay, no units for pH. And then the last one, what's the pH of a 3.2 molar nitric acid solution? So what we need to do here is we need to look, okay, I don't know what the H plus concentration is, but I'm going to look at my equation for the dissociation of nitric acid. Nitric acid is a strong acid and therefore will dissociate into its 2 ions. Now, if this is 3.2 molar, it's going to break up into 3.2 molar of this and 3.2 molar of that because it's a 1-to-1 ratio. For every one of those, I get one of those and one of those. And so then we just say pH is equal to the negative log of 3.2, which is -0.51. Okay, pretty simple. We can also do the POH, which is the same thing, except now you have the hydroxide ion concentration. So the POH is equal to the negative log of the hydroxide ion concentration. Now, if I know the POH, I can solve for the pH. pH plus POH equals 14, and therefore you can solve that. So this one here, I have 0.08 molar of sodium hydroxide. Sodium hydroxide will dissociate completely into its ions. And therefore, the POH is the negative log of 0.08 molar, which is 1.10. So that means the pH is equal to 14 minus 1.10, which is 12.9, which should make sense to you. 12.9 is a very strong base, and we know sodium hydroxide is a strong base. So now for the next one, it's going to be different only because of the formula. Calcium hydroxide, when it dissociates, will turn into 2 hydroxide ions. So if this is 3.8 times 10 to the negative 4, this would be 3.8 times 10 to the negative 4. This would be 2 times 3.8 times 10 to the negative 4. So you got to look at that stoichiometric relationship, and then we just do the same steps. POH is equal to the negative log of 7.6 times 10 to the negative 4, which equals 3.12, and therefore the pH is 14 minus 3.12, which is 10 point, no, not 18, 10.88. Okay, so again, don't just assume you just take the negative log and you're done. Look at the formula, look to see if there's a weird ratio, and then if you're doing a base, make sure you do 14 minus the POH. All right, so there are acids that will dissociate more than one hydrogen. Those are called diprotic acids, di for 2 hydrogens. If you have more than 2 hydrogens, like 3 hydrogens in phosphoric acid, that's called a polyprotic acid. So again, the main point here is make sure that you're looking at your ratio. Okay, so I've got sulfuric acid will decompose in, no, stop saying decompose, dissociate into 2 hydrogen ions and a sulfate ion. So if this is 3.9 times 10 to the negative 4th, this is 2 times 3.9 times 10 to the negative 4th. So we're just going to find pH, negative log of 2 times 3.9 times 10 to the negative 4th is 7.8 times 10 to the negative 4th. And so my pH will be 3.11. Pretty simple. So if I want to find the hydrogen ion concentration of a solution with 3.9 pH, remember the concentration of the H plus ion is equal to 10 raised to the negative pH. So that's going to be 10 raised to the negative 3.9, which gives me 1.26 times 10 to the negative 4th. Now here, we're doing hydrogen ion concentration, so you must include that unit of molar. Same thing here. H plus is going to be equal to 10 raised to the negative 13.5. And that gives me 3.16 times 10 to the negative 14th molar. So this is very basic, which means I have a very low hydrogen ion concentration. Okay, just some examples. Now, so finding the pH of a strong acid, strong base, very simple, negative log, whatever, do all those steps. Now, if I have a weak acid or a weak base, I have to use a Rice table. Now, for some reason you aren't going in order of the videos, you really do need to watch last week's video in order to be able to do a Rice table for acids and bases. It's the same thing. So I'm going to kind of go fast through this since you should already have an understanding of what a Rice table is and how it works. So I want to know the pH of a 1.5 times 10 to the negative 3rd molar acetic acid solution with a Ka of 1.8 times 10 to the negative 5th. Okay, so R, the R in my Rice table stands for the reaction. So I'll take the acetic acid. Oh, that's so bad. I will dissociate into the H plus and the CH3, the acetate ion. Now you can include water, but you don't have to because acids will give off that hydrogen, which is what I need in order to solve. You'll see in the next one, for a base example, you have to include the water so that you can have the hydroxide ion. Initially, I have 1.5 times 10 to the negative third molar. Remember, I stands for initial concentration. I have none of this to start with. My change, well, I'm going to lose this and I'm going to gain this. And remember, the x's have to do with the coefficients in your balanced equation. They're all 1, so I'm losing that and gaining 1 hydrogen. Well, well, 1 of however many hydrogens, and then the same for the acetate. And remember, for E stands for at equilibrium. You take the I and the C and you combine them. 1.5 times 10 to the negative third minus x. This can just be x, and this can be x. So the next thing you want to do is write out your Ka expression, okay? Because we have a Ka, we need to use it in order to solve for the hydrogen ion, and so then we can go ahead and find the pH. So the Ka, again, Ka, concentration of products raised to their coefficients divided by concentration of reactants raised to their coefficients. It's going to be H plus CH3COO minus over CH3COOH. Okay? And just like earlier in the previous examples, we always use our E value for our Ka. Remember, since my Ka is to the negative fifth, it's very small, I can negate or neglect that minus x, and therefore do not have to do a quadratic. Remember, you are not required to do a quadratic. You should always be able to neglect that. I did post a link in last week's assignment where you can go and see a video where they do not neglect the x and where they do neglect the x and how little the answers change. So I'm going to just fill in the information I have. I know the Ka is 1.8 times 10 to the negative fifth. That's going to be, it's x times x, which is x squared, over 1.5 times 10 to the negative third. So what I want to do, multiply both sides by 1.5 times 10 to the negative third, and then take the square root. When I do that, I will solve for x, which is the H plus concentration, which you should get as 1.6 times 10 to the negative fourth molar. Okay, make sure you can do that math. Pause the video, do the math, make sure you can get that value as x. Then I'm not finished yet because the answer to the question is what is the pH? So now I just say pH is equal to the negative log of the H plus concentration, which was 1.6 times 10 to the negative 4. And so the answer to this question is going to be 3.78. Okay, not terrible. Make sure you can do that. If you have questions, please ask. Again, it's just a rice table. And so the last thing that we'll do today is we'll do an example with a base, a weak base that will not dissociate completely. And in this case, it's going to be methylamine. So a solution, no, it says calculate the pH of a 1.00 molar solution of methylamine with a Kb of 4.38 times 10 to the negative fourth. Okay, not a problem. We just start with our R, methylamine. I have to include the water here because when I put this into equilibrium, the methylamine is the base, which means the water is the acid. The acid will give off an H and become OH minus, which I need because I'm talking about a base here. And my product, my other product will be H3 with a plus, okay? So initially, I've got 1.00 molar. I've got 0 of this, 0 of this. Now what I do with the water, I just draw a straight line. I don't care about the water at all. It does not go into any of the calculations for this. C, again, it's all 1-to-1, so I'm going to be losing the reactant and gaining the products. And then E, 1.00 minus X, X, and X. Now, instead of doing a KB, I do a K. Instead of doing a KA, I'm doing a KB here. But same thing, concentration of the products raised to their coefficients divided by concentration of reactants raised to their coefficients. Remember, solids and pure liquids are not included, and that's another reason why we put a line here, because we don't want to include water. So it's going to be the hydroxide ion concentration times the other ions concentration over CH3 and H2. Okay. Again, we have a very small KB. It's to the -4th. I'm going to neglect that. So I know KB is 4.38 times 10 to the -4th. That will be equal to, again, that's x squared over 1.00. It's not always going to be x squared, but a lot of the times it's going to be x squared. It might be 2x squared. Pay attention to that. It depends on your ratio. When you rearrange and solve for x, x will give me the hydroxide ion concentration, which is the thing I care about, which is going to be 2.09 times 10 to the -2nd molar. Then I can calculate the POH, which is going to be 1.68, and therefore the pH is going to be 12.32. There you go. That's it for this week's notes. Next week, we'll talk about titrations. Next week, which is the last week, by the way, we'll talk about titrations, and you'll have an online lab to do, because the titration is a very important lab-based skill to have. All right, I'll see you next week.